Assalamu alaikum. Good morning, everyone. So I am continuing on the lecture about crystalline state and solid state. This is lecture 11, where I am continuing to talk about the ionic crystal structures. In my lecture 10, I covered metallic crystal structures. Just as a recap, a quick recap, let me just go. Yeah. As a recap, previously I described the four types of crystals. We have metallic crystals, which I have shown you in lecture 10, how to calculate number of particles, how to use density to determine the type of metals, and how to use the information to determine the radii or the atomic radius of a metal atom. Now, this lecture 11 of CHM 577, I'm going to talk about ionic crystals. Ionic radii and ionic crystal structures. Obviously, everybody knows when you have ions interacting together to form a solid, so they make ionic solid. And ionic solids are made up of cations and anions, positively charged ions and negatively charged ions, which are alternately arranged in 3 dimensions, and they are held by ionic bond. Now, the structure of a particular crystals depend on the relative sizes of cations and anion. When we talk about ionic crystals, it's quite different from, a little bit different from the metallic crystals that we described in lecture 10. When we talk about ionic crystals, you have to look at the relative sizes of your cations and your anions. Generally, cations are always smaller than anions. A positively charged ion is usually smaller than your negatively charged ions. And we have described, I have explained that to you in my, I don't know, maybe lecture 2, something like that. And the relative sizes of these ions will, they are represented by the radii, and they will determine what type of ionic crystals you will get. The ratio of the radius of the cation divided by the radius of the anion will determine the type of crystal structure of the ionic compound that you will get. So how is that done? So if the radius of your cation, you divide it by the radius of your anion, oh, that should be, yep. When the value of this radius falls between 0.225, excuse me, 0.225 to 0.414, where the anion is much, much, much bigger than the cation, then you are going to have the lattice type of ZnS or zinc blend. When your anion is so much bigger than your cation, and the coordination number that you get is obviously for later, you are going to get what is called the ionic lattice type of zinc blend. But if the cation is a little bit bigger, but the anion is still obviously bigger than the cation, but not that much bigger, or the ratio between R radius of cation and radius of anion falls between 0.4 to 0.7, you are going to get a lattice which is called rock salt or sodium chloride, because the difference, the sodium and the chloride, when you divide their radius, you're going to get a value between 0.414 and 0.732. Unlike zinc and sulfide or zinc blend, you get this radius ratio. But when your anion is almost the same size as your cation, where you have R plus divided by R minus is between 0.7 to 1, they are almost of similar type, similar size. Then you get this lattice type, which is called the cesium chloride, CsCl, and coordination number of 8. I'm going to describe to you what is this coordination number. What does it mean? Yeah. So when your anion is much bigger than your cation, you get zinc blende or ZnS. When your anion is almost the same size as your cation, you get the structure of cesium chloride, CsCl. But in between those two, you are going to get the structure of rock salt or sodium chloride structure. Okay, I'm going to start with zinc blende. Now, zinc blende or zinc sulfide, it crystallizes into two different forms depending on temperature. One is called the woodsite structure. Another one is called the zinc blende structure. The key difference between zinc blende and woodsite is that zinc blende is cubic and woodsite is hexagonal. Remember when we talk about the metal crystals, when you have AB, you get cubic, ABC, you get hexagonal. So that is exactly what is happening with this ionic compounds with a zinc blende structure, where your woodsite will assume a hexagonal structure and your zinc blende will assume a cubic structure. But never mind about that one. The ionic radius of zinc 2 ion is 0.474 angstrom, and sulfide ion is 1.90 angstrom. When you divide the cation by the anion, you are going to have a value of 0.39. Yeah. 0.39 it falls between this ratio, 0.414, 0.225. It really shows that your cation is so much smaller than your anion. So you have that particular salt to assume the structure of ZnS. So not necessarily zinc and sulfide only. It could be others, very big metal and very small, a very big metal cation and very small non-metal anions that will fall into the zinc blende structure, as long as the ratio is between 0.4.4 to 0.225. You're going to get a zinc blende structure. Now, this is the zinc blende structure. The sulfide ion, which is the one on the corner, this yellow, is always bigger. Remember, your anions are always bigger than your cations. The sulfide ions lie in a cubic closed pack arrangement. The zinc 2 ions are much smaller than the sulfide ions. The insertion of zinc 2 ions into the tetrahedral hole causes the structure to expand so that the sulfide ions are not in contact with each other. Zinc blende has a 4-4 coordination. That means the zinc is touching for sulfide and the sulfide is touching for zinc. The 4 zinc ions are contained within the cells, and the sulfide ions form a FCC, facial cubic close packing structure. Yeah. And you see that all this yellow, they look like an FCC, face cubic structure arrangement, whereas your zinc is right in the middle of the cell. So this is the structure of a zinc blende. We're not going to go into woodsite. We just go into zinc blende for now. Woodsite is somehow out of this syllabus, yeah? Now, the coordination number of each of the cations and the anions in zinc blende is 4. The number of ions of the opposite charge touching one particular ion is equal to 4. Can you see here that if we take, that one there, that zinc white ion there, it is touching 1, 2, 3, and 4 sulfide. So the coordination number of zinc is 4. And similarly, if you take this sulfide right there, it is touching 4 zinc. So it is 4, 4. In a ZnS or zinc blende structure, there are 8 anions occupying the corners of the cube, and there is 1 cation at the center of the cube. So, not 1, 4. Not 1, there are 4 here. Excuse me, that's the wrong one there. 4 cations at the center of the cube. So the net number of anions is 4 times 1.8 plus 6 times 1 over 2. Remember the phase, yeah, is equal to 4. The number of cations, the 4 right in the middle, is equal to 4 times 1. So total number of ions is 4 cation and 4 anion, altogether 8 ions in 1 unit cell for the zinc blende, when you have the cation so much smaller than your anions. Now go to the next one, is when you have the cation still smaller than the anion but not too much smaller, yeah, then the structure will assume a structure of sodium chloride, because if you take the ratio of radius of sodium divided by radius of chloride, you are going to have a value between 0.732 to 0.414, and any combination of cations and anions that have this ratio between 0.732 to 414, they will assume the structure of sodium chloride. Now, this structure is sometimes referred to as the rock salt structure, and the size of sodium cation is smaller than the size of the chloride anion, and this is what it looks like. This is what a sodium chloride structure looks like. If you remember, the zinc blende is a lot more different. Yeah, this is zinc blende, very different compared to the sodium chloride. Now, in the sodium chloride, the sizes of the ions are different. The cations, which are black, and the anions, which are white, they are packed closely in a triangular arrangement in one layer as shown below. And the layers are then stacked on top of one another, with each layer occupying the depressions on the other layer. So when there is a depression, then there is an ion sitting at the top of it or at the bottom of it. Yeah. When you have a first layer arranged in this way, where you have white, black, white, black, white, black, or anion, cation, and so on and so forth, and you put the second layer up on top of it, exactly the opposite, you're going to have a structure which looks like this. Yeah, the structure which looks like this, like that. And this is called the rock salt structure or sodium chloride structure. So what does a sodium chloride unit cell look like? It looks like this. So this is a little bit easier for you to look the one on the right hand side of this slide, where you have the green. The green is chloride and the brown is sodium. The chloride ions occupy the face-centered cubic lattice. It looks like a face-centered cubic lattice. And the sodium ions are alternately placed in between the anions. Where there is a space between the anions, you put a sodium ion. So this is the structure of a rock salt. So if you look at this extended lattice, just take 1, 2, 3, 4, 5, 6, 7, and 8. There's one extra layer here. You will be able to see that your chloride right there in the middle is connected to 1, 2, 3, 4, 5, and 6 sodium. And similarly, your one sodium is connected or touching 4 different chloride. So that is the structure of the sodium chloride. No, not 4, 6, yeah. The big difference in the sizes of the cation and anion allows the much smaller cation to occupy the holes between the much bigger anions. And this arrangement allows for a close packing of ions. And number of the coordination number, which is the number of ions of the opposite charge touching one particular ion, is equal to 6, like I counted before in here. Right. Sodium chloride. How do you count the number of sodium ion and the number of chloride ion in one unit cell of rock salt? You just have to count it like this. There are 8 anions occupying the corners of the cube, 6 anions occupying the surfaces of the cube. There are 12 cations occupying the edges of the cube and 1 cation right there in the middle. So to count the number of anions is 8 times 1/8, yeah, plus 6 times a half, that's 4. For cations, you have 12 on the edge, so 12 times a quarter, plus 1 right there in the middle. So that is 4. So the ratio is always 1 to 1, 4 with 4. Same with your cesium chloride just now. It's also 4 with 4. No, not cesium chloride, zinc blend, 4 with 4. Yeah, so still 1 to 1 ratio. So the total number of ions is 4 cations and 4 anions, making 8 ions altogether. And lastly, when we talk about a situation where your cation is almost the same size as your anion, that the structure will assume a cesium chloride structure. The size of cesium cation is not very different from the size of your chloride anion. So you have the radius ratio of 1 to 0.732, and this is the structure of cesium chloride as shown below. So it's probably not very clear here. It is like this. It is a body-centered cubic, lebih kurang. Yeah, it's almost like that. So cesium chloride, where the cesium is so much, not too much smaller than your chloride. First of all, you have your chloride sitting in the first layer, and then you are arranging your cesium on the second layer in this manner, where there is a depression, you put a cesium in, and then the third layer like that. So it's AB, AB, and you get a cesium chloride structure. It's almost like a body-centered cubic. So this is the formation of a cesium chloride crystal structure. And how do you count the number of ions or anions in the cesium chloride structure? Well, before we count the anions, we just have to look at the coordination number. The number of ions of the opposite charge touching one particular ion is 8. This is really, really very easy to see in this case. You have 1 cation right there in the middle with 8 anions touching it, one from each corner of the cube. So you have 8 anions occupying, and there are 8. And similarly, when we talk about the anion, it will be touching 8 cations. When we talk about cations, it will be touching 8 anions, right? So that is the coordination number. For cesium chloride structure, there are 8 anions occupying the corners of the cube. There is 1 cation at the center of the cube. So it's really very simple to calculate. Anions 8 times 1/8 equals to 1. Cations is simply 1. So number of ion is 1 anion to 1 cation. It's still 1 to 1 ratio. So you have your zinc blend, you have your rock salt, and you have your cesium chloride structure. So as a summary, when you have your anion so much bigger than your cation, you're going to have a zinc blend structure where coordination number is 4, number of cation is 4, number of anion is also 4. When you have the cation still smaller than your anion, but not too much smaller, you have the ratio between 0.414 to 0.732. The coordination number of each of those ions will be 6, and it's going to assume the rock salt structure or sodium chloride. Number of cations is 4, counted in that way. Number of anions is another 4 counted in the other way. And this is the structure. That's your zinc blend. This is your rock salt structure. And lastly, when your anion and your cation have almost similar sizes, you are going to have a cesium chloride lattice type with coordination number of 8 for each ion, and number of cation is 1, number of anion is 1, also like so. So that is the summary. So for density calculation, I'm going to show you the density calculation. Oops. Now, to calculate the density of ionic solids that has sodium chloride structure, the edge length of the unit cell must be found, since the cation is nearest and its nearest neighbors anions are, in definition, in contact. Therefore, the cell edge length of sodium chloride is given like this. So if you look at this structure, this is your anion with 1 radius. That is your cation with 2 radius of your cation. And then there's another anion on the left-hand side with another radius. So A, which is the edge length of this cube, is 2 times the radius of the cation plus 2 times the radius of the anion. So that is how you are going to calculate the radius of your anions and your cations by this. And there is one example for density calculation. Knowing the number of ions in a unit cell, the density of solid sodium chloride can be calculated as explained earlier. Example is the edge length of sodium chloride unit cell is 564 picometers. Remember, 1 picometer is 10 to the power of minus 12 meters. I always tell you, convert everything into centimeter when you go into density calculation. So the question is, what is the density of sodium chloride in gram per centimeter cubed? So obviously your volume is very easy. 564 picometers is equal to 564 times 10 minus 10 centimeters. Yeah. You cube that, you get the volume. The mass, you know that there are 4 sodium and there are 4 chloride. So 4 sodium is 4 times 23 atomic mass unit, and chloride is 4 times 35.5 atomic mass unit. So the mass per unit cell is 234 atomic mass unit. And we know 1 mole is Avogadro's number. So use that formula that I described earlier in lecture 10. Density is equal to mass over volume. So your mass is 234 AMU divided by Avogadro's number divided by your volume, which is this one. So you get the density of sodium chloride salt to be 2.17 gram per centimeter cubed. So that is one worked example. I hope you understand that worked example, because you have a practice 3 that you have to work it out. In rubidium bromide crystal, the size of rubidium plus, so this should be superscript, and Br minus ions, are almost the same, and the R plus divided by R minus is bigger than 0.732. So what is this information telling us? Go back here. When it is bigger than 0.732, then it's going to assume a cesium chloride lattice type, and this is what the drawing will look like, the drawing of your unit cell. So, question is, given that the radii of rubidium plus and bromide minus are 148 picometers and 195 picometers respectively, first of all, name the structure of rubidium bromide. Very easy, right? draw the unit cell of rubidium bromide and label the positive and negative ion. Very easy, very simple. And calculate the age length and density of rubidium bromide. I have the answer here. You try to work it out. And if you don't get the answer, ask me later, or you want to check your answer whether it's correct or not, ask me later, and we are going to have a discussion about this in class. So I think that just about wraps up. This is about 25-minute lecture. Wraps up about the ionic crystals. Yeah. So it's really very simple. There is no discussion about simple molecule crystal, but my next lecture, which is lecture number 12, will be on macromolecular crystals. In the meantime, have a good learning session, and I hope you understand everything that I have described in this lecture 11. Goodbye, everyone. Take care and be safe. Assalamualaikum.